Welcome to aminacademy.com. Let us do mini tour on physics regarding history of physics. Now we'll do physics, the natural science that studies matter, its fundamental constitutes its motion and behavior through space and time, and the related entities of energy and force. Physics is one of the most fundamental scientific discipline, with its main goal being to understand how the universe behaves. Elements of what became physics were drawn primarily from the field of astronomy, optics, and mechanics, which are methodologically united through the study of geometry. These mathematical disciplines began in antiquity with the Babylonians and with Hellenistic writers such as Archimedes and Ptolemy. Usually physics starts from the age of Ptolemy. Claudius Ptolemy, who wrote about the dozen scientific treatises, three of which were of importance to later Byzantine, Islamic, and Western European sciences. The philosopher Thales of Miletus, 7th and 6th centuries, dubbed the father of science for refusing to accept various supernatural, religious, or mythological explanation for natural phenomena, proclaimed that every event had a natural cause. Around 500 BCE, Heraclitus proposed that the only basic law governing the universe was the principle of change, and that nothing remains in the same state indefinitely. This observation made him one of the first scholars in the ancient physics to address the role of time in the universe, the key and sometimes contentious concept in modern and present day physics. Hipparchus, focusing on astronomy and mathematics, used sophisticated geometrical techniques to map the motion of the stars and planets, even predicting the times that solar eclipse would happen. Ptolemy, one of the leading minds during the time of Roman Empire, Ptolemy was the author of several scientific treatises, at least three of which were important. And in Indian astronomy, Aryabhatiya proposed the Earth's rotation. In Islamic world, Ibn al-Haytham is very important scientist. Ibn al-Haytham, 965 to 1040, an Arab scientist considered to be a founder of modern optics. Ibn al-Haytham and Biruni were early proponents of the scientific methods. Ibn al-Haytham is considered to be by some the father of modern scientific method due to his emphasis on the experiment date and reproducibility of the result. Ibn Sina, 980 to 1037, known as Avicenna, was a polymath from Bukhara. In present day, it's in Uzbekistan, responsible for important contribution to physics, optics, philosophy, and medicine. He published his theory of motion in Book of Haley. Hibat Allah Abu Barakat al-Baghdadi, 1082 1165, adopted the modified Ibn Sina's theory of projectile motion. Nasir al-Din al-Tusi, a Persian astronomer and mathematician who died in Baghdad, introduced the Tusi couple. Copernicus later drew heavily on the work of al-Din al-Tusi and his student, but without acknowledgement. Celestial objects were described as moving in circle because perfect circular motion was considered an innate property of objects that exist in the uncorrupted realm of the celestial sphere. Now we are dealing with the history of scientists in short form. During 16th to 17th centuries, a large advancement of scientific progress known as the scientific revolution took place in Europe. The Polish astronomer Nicolaus Copernicus is remembered for his development of heliocentric model of the solar system. Breakthrough in astronomy was made by Polish astronomer Nicolaus Copernicus when in 1543 he gave strong argument for the heliocentric model of the solar system. On the Revolution of the Celestial Spheres was published just before his death in 1543, and as it is now generally considered to mark the beginning of modern astronomy, it is also considered to mark the beginning of the scientific revolution. Copernicus' new perspective, along with the accurate observation made by Tycho Brahe, enabled German astronomer Johannes Kepler to formulate his law regarding planetary motion that remains in use today. Now, next very important hero, Galileo Galilei, early proponent of the modern scientific worldwide and method. The Italian mathematician, astronomer and physicist Galileo Galilei, 1564 to 1642, was famous for his support of Copernicanism, his astronomical discoveries, empirical experiment, and his improvement to the telescope. Galileo has been called the father of modern observational astronomy, the father of modern physics, and the father of science, and the father of modern science. According to Stephen Hawking, Galileo, perhaps more than any other single person, was responsible for the birth of modern science. As religious orthodoxy decreed a geocentric or trichonic understanding of the solar system, Galileo's support for heliocentrism provoked controversy, and he was tried by the Inquisition. Found vehemently suspect of heresy, he was forced to recant and spent the rest of his life under house arrest. The contribution that Galileo made to observational astronomy include the telescopic confirmation of the face of Venus. His discovery in 1609, the Jupiter's 4 largest moons, subsequently given the collective name of the Galilean moons, and the observation and analysis of sunspots. Galileo also pursued applied science and technology, inventing, among other instruments, a military compass. His discovery of the Jovian moons was published in 1610. Still more information about the Galileo is there. René Descartes, the French philosopher René Descartes, was well connected to influential within the experimental philosophy network of the day. Christian Huygens, the Dutch physicist, mathematician, astronomer, and inventor Christian Huygens was the leading scientist in Europe between Galileo and Newton. Next, our hero, Isaac Newton. The late 17th and early 18th centuries saw the achievement of Cambridge University physics and mathematician Sir Isaac Newton, 1642 to 1727. Newton, a fellow of Royal Society of England, combined his own discoveries in mechanics and astronomy to earlier ones to create a single system for describing the working of the universe. Newton formulated 3 laws of motion, which formulated the relationship between motion and objects, and also the law of universal gravitation, the latter of which could be used to explain the behavior not only of falling bodies on the earth but also planets and other celestial bodies. To arrive at his result, Newton invented one form of an entirely new branch of mathematics, that is calculus, also invented independently by Gottfried Leibniz, which was to become an essential tool in much of the later development in most branches of physics. That is, calculus is very important branch of mathematics which is useful in physics. Newton's findings were set forth in his Philosophia Naturalis Principia Mathematica, that is, mathematical principles of natural philosophy, is publication of which in 1687 marked the beginning of the modern period of mechanics and astronomy. Newton, who was also deeply interested in theology, imagined that God intervened to ensure the continued stability of the solar system. Next, Gottfried Leibniz. Newton's principle, but not his mathematical treatment, proved controversial with continental philosophers who found his lack of metaphysical explanation for movement and gravitation of philosophically unacceptable. Newton built the first functioning reflecting the telescope and developing the theory of color published in optics, based on observation that prism decomposes white light into many colors of forming visible spectrum, while Newton explained light as being composed of tiny particles. A rival theory of light, which explained its behavior in terms of waves, was presented in 1690 by Christian Huygens. Also formulated an empirical law of cooling. Newton also formulated an empirical law of cooling, studied the speed of sound, investigating power series, demonstrated the generalized binomial theorem, and developed a method for approximating the roots of function. Other branch of physics also received attention during the period of the scientific revolution. Robert Boyle studied the behavior of gases enclosed in a chamber and formulated the gas law, named for him. He also contributed to physiology and to the founding of modern chemistry. Early thermodynamics. A precursor of the engine was designed by the German scientist Otto von Guericke, who in 1650 designed and built the world's first vacuum pump to create a vacuum, as demonstrated in the Magdeburg hemispheres experiment. Engineer Thomas Savery built the first engine. The main problem with this first engine was that they were slow and clumsy, converting less than 2% of the input fuel into useful engine. In other words, efficiency is very, very less. Alexander Volta. During the 18th century, the mechanics found by Newton was developed by several scientists as more mathematicians learned calculus and elaborated upon its initial formulation. The application of mathematical analysis to problems of motion was known as rational mechanics or mixed mathematics and was later termed classical mechanics. In classical mechanics, Daniel Bernoulli is important figure. In 1714, Brooke Taylor derived the fundamental frequency of stretched vibrating string in terms of its tension and mass per unit length by solving a differential equation. The Swiss mathematician Daniel Bernoulli made important mathematical studies of the behavior of gases. Anticipating the kinetic theory of gases developed more than a century later, he has been referred to as the first mathematical physicist. During 18th century, thermodynamics was developed through the theories of weightless, imponderable fluids such as heat. The heat is considered as imponderable fluid, and electricity and phlogiston, which was rapidly overthrown as a concept of following Lavoisier's identification of oxygen gas late in the century. Benjamin Franklin's characterization of electrical fluid as flowing between places of excess and deficit, a concept later reinterpreted in terms of positive and negative charges. Franklin also showed that lightning is electricity in 1752. Experiments in mechanics, optics, magnetism, static electricity, chemistry and physiology were not clearly distinguished from each other during the 18th century, but significant differences in explanatory schemes and thus experiment design were emerging. Chemical experiments, for instance, defined attempt to enforce the scheme of abstract Newtonian forces onto chemical affiliations, and instead of focused on the isolation and classification of chemical substances and reactions. 1821, William Hamilton began his analysis of Hamilton's characteristics function. In 1835, he stated Hamilton's canonical equation of motion. Peter Ewart supported the idea of the conservation of energy in his paper on the measure of moving force. Michael Faraday. In 1800, Alexandro Volta invented the electric battery known as the voltaic pile and thus improved the way electric current could also be studied. 1831, Faraday and independently Joseph Henry discovered the reverse effect, that production of an electrical potential or current through the magnetism, known as electromagnetic induction. These two discoveries are the basis of the electric motor and electric generator respectively. In the 19th century, the connection between heat and mechanical energy was established quantitatively by Julius Robert von Mayer and James Prescott Joule, who measured the mechanical equivalent of heat in 1840s. Sadi Carnot work provided a basis for the formulation of the first law of thermodynamics, a restatement of the law of conservation of energy. statistical mechanics, that is a fundamentally new approach to the science. In 1859, James Clerk Maxwell discovered the distribution law of molecular velocities. Maxwell showed that electric and magnetic fields are propagated outward from their source at a speed of equal to that of light, and that light is one of the several kinds of electromagnetic radiation, differing only in the frequency and wavelength from the others. In 1859, Maxwell worked out of the mathematics of the distribution of velocities of the molecules of a gas. The wave theory of light was widely accepted by the time of Maxwell's work on the electromagnetic field. In the mid to late 1890, Guglielmo Marconi developed a radio wave-based wireless telegraphy system. The atomic theory of matter had been proposed again in the early 19th century by the chemist John Dalton and became one of the hypotheses of the kinetic molecular theory of gases developed by Clausius and James Clerk Maxwell to explain the law of thermodynamics. The kinetic theory in turn led to revolutionary approach to science, the statistical mechanics of Ludwig Boltzmann, Josiah Willard Gibbs, which studied the statistics of microstates of a system and uses statistics to determine the state of physical system. In 1822, botanist Robert Brown discovered Brownian motion, pollen grain in water undergoing movement resulting from their bombardment by the fast-moving atoms or molecules in the liquid. In 1842, Christian Doppler proposed the Doppler effect. At the end of 19th century, physics had evolved to the point at which classical mechanics could cope with highly complex problems involving macroscopic situations. Thermodynamics and kinetic theory were well established. Geometrical and physical optics could be understood in terms of electromagnetic waves, and the conservation of laws for energy and momentum and mass were widely accepted. So profound were these and other developments that it was generally accepted that all the important laws of physics had been discovered, and that henceforth research would be concerned with cleaning up minor problems and particularly with improvements of method and measurements. However, around 1900, serious doubts arose about the completeness of the classical theories, and triumph of Maxwell's theories, for example, was undermined by inadequacies that had already begun to appear, and their inability to explain certain physical phenomena such as the energy distribution in blackbody radiation and the photoelectric effect, while some of the theoretical formulations led to paradoxes when pushed to the limit. Prominent physicists such as Heinrich Lorentz, Emil Kohn, Ernest Weichert, and Wilhelm Wien believed that some modification of Maxwell's equation might provide the basis for all physical laws. The shortcomings of classical physics were never to be resolved, and new ideas were required. At the beginning of 20th century, a major revolution shook the world of physics, which led to a new era, generally referred as a modern physics. J.J. Thomson in 1856 to 1940 discovered the electron and isotopy of, and also invented the mass spectrometer. He was awarded the Nobel Prize in Physics in 1906. In the 19th century, experiments began to detect unexpected forms of radiation. Wilhelm Röntgen caused a sensation with his discovery of X-rays in 1895. In 1896, Henry Becquerel discovered that certain kinds of matter emit radiation on their own accord. In 1897, J.J. Thomson discovered the electron, and new radioactive elements found by Marie and Pierre Curie raised questions about the supposedly indestructible atom and the nature of matter. Marie and Pierre coined them radioactivity to describe this property of matter and isolated the radioactive elements, that is radium and polonium. Ernest Rutherford and Frederick Soddy identified two of Becquerel's forms of radiation with electrons and the elements helium. Rutherford identified and named two types of radioactivity, and in 1911 interpreted experimental evidence as showing that the atom consists of a dense positively charged nucleus surrounded by negatively charged electrons. Classical theory, however, predicted that this structure should be unstable. Classical theory had also failed to explain successfully two other experimental results that appeared in the late 19th century. One of these was the demonstration by Albert M. Michelson and Edward W. Morley, known as Michelson-Morley experiment, which showed there did not seem to be a preferred frame of reference at rest with respect to the hypothetical luminiferous ether for describing electromagnetic phenomena. Studies of radiation and radioactivity decay continued to be a preeminent focus for physical and chemical research through the 1930s, when the discovery of nuclear fission by Lise Meitner and Otto Frisch opened the law to the practical exploitation of what came to be called atomic energy. Now, Albert Einstein's theory of relativity, the superhero Albert Einstein. In 1905, a 26-year-old German physicist named Albert Einstein, then patent clerk in Bern, Switzerland, showed how measurements of time and space are affected by motion between an observer and what is being observed. Einstein's radical theory of relativity revolutionized the scene. Although Einstein made many other important contributions to science, the theory of relativity alone represents one of the greatest intellectual achievements of all time. Although the concept of relativity was not introduced by Einstein, he recognized that the speed of light in vacuum is constant, that is the same for all observers, and an absolute upper limit to speed. This does not impact a person's day-to-day life, since most objects travel at speed much slower than light speed. More objects traveling near light speed. However, the theory of relativity shows that clocks associated with those objects will run more slowly and that the objects shorten in length according to measurements of an observer on Earth. Einstein also derived the famous equation E equal to mc squared, which expresses the equivalence of mass and energy. Now, Einstein's special relativity. Einstein proposed that gravitation is a result of masses or their equivalence energies curving, bending the space-time in which they exist, altering the path they follows with it. Einstein argued that the speed of a light was a constant in all inertial reference frames and that electromagnetic law should remain valid independent of reference frame assertions, which rendered the the ether superfluous to physical theory, and that held that observation of time and length varied relative to how the observer was moving with respect to the object being measured, what came to be called the special theory of relativity. It also followed that mass and energy were interchangeable quantities according to the equation E equal to mc squared. In other words, paper published the same year, Einstein asserted that electromagnetic radiation was transmitted in discrete quantities, that is quanta, according to a constant that the theoretical physicist Max Planck had posited in 1900 to arrive at an accurate theory for the distribution of black body radiation, an assumption that explained the strange properties of the photoelectric effect. The special theory of relativity is a formulation of the relationship between physical observation and the concept of space and time. Here, a question arises. It arises out of the questions: what is time? Newton in the Principia had given an unambiguous answer: absolute, true, and mathematical time of itself and form its own nature, flows equably without relation to anything external, and by another name is called the duration. This definition is basic to all classical physics. That is here what we done here. That is what is time. Ask the definition. To the definition, Newton says like, but Einstein had the genius to question it and found that it was incomplete. Instead, each observer necessarily makes use of his or her own scale of time. That means each person has his own time when they travel very fast. And for two observers in relative motion, their time scale will differ. This induces a related effect on position measurements. Space and time becomes intervened concept, fundamentally depends on the observer. Each observer presides over his or her own space-time framework or coordinate system. There being no absolute frame of reference, all observers of given events make different but equally valid and reconcilably measurements. What remains absolute is stated in Einstein's relativity postulates that the basic law of physics are identical for two observers who have a constant relative velocity with respect to each other. General relativity. By 1916, Einstein was able to generalize this further to deal with all states of motion, including non-uniform acceleration, which becomes a general theory of relativity. In this theory, Einstein also specified a new concept, the curvature of space-time, which describes the gravitational effect at every point in space. In fact, the curvature of space-time completely replaced Newton's universal law of gravitation. According to Einstein's, gravitational force in the normal sense is a kind of illusion caused by the geometry of space. The presence of mass causes a curvature of space-time in the vicinity of the mass, and this curvature dictates the space-time path that all freely moving objects must follow. It was also predicted from this theory that light should be subject to gravity, all of which was verified experimentally. The gradual acceptance of Einstein's theories of relativity and quantized nature of light transmission, Niels Bohr's model of the atom created as many problems as they solved, leading to full-scale effort to re-establish physics on new fundamental principles, expanding relativity to causes accelerating reference frame. That is called in general theory of relativity. Quantum mechanics. Although the relativity resolved the electromagnetic phenomena conflict demonstrated by Michelson and Morley, a second theoretical problem was the explanation of the distribution of electromagnetic radiation emitted by black body. Experiments showed that at shorter wavelengths towards the ultraviolet end of the spectrum, the energy approached zero, but classical theory predicted it should become infinite. This glaring discrepancy known as the ultraviolet catastrophe. Werner Heisenberg. In 1905, Einstein used the quantum theory to explain the photoelectric effect, and in 1913, the Danish physicist Niels Bohr used the same constant to explain the stability of Rutherford's atom as well as the frequencies of light emitted by hydrogen gas. Heisenberg in 1927 uncertainty principles including the impossibility of precisely and simultaneously measuring position and momentum, and the Copenhagen interpretation of quantum mechanics named after Bohr's home city, continued to deny the possibility of fundamental causality, though opponents such as Einstein's would metaphorically assert that God does not play dice with the universe. Quantum field theory. A Feynman diagram represents left to right the production of photon, blue sine wave, from the annihilation of electron and its complementary antiparticles, the positron. The photon becomes a quark antiquark pair, and gluon, green spiral, is released. As the philosophically inclined continued to debate the fundamental nature of the universe, quantum theories continued to be produced, beginning with Paul Dirac's formulation of the relativistic quantum theory in 1928. However, attempts to quantize electromagnetic theory entirely were seemed throughout the 1930s by theoretical formulation yielding infinite energies. Unified theories. Einstein deemed that the fundamental interaction in nature can be explained in a single theory. Unified field theories were numerous attempts to merge several interactions, one of many formulations of such theories, as well as field theories in general, is a gauge theory, a generalization of the idea of symmetry. Eventually, the standard model succeeded in unification of strong, weak, and electromagnetic interaction. All attempts to unify gravitation with something else failed. Formation of the unification of the electromagnetic and weak interaction in the standard model is due to Abdussalam, Steven Weinberg, and subsequently Sheldon Glashow. Electro-weak theory was later confirmed experimentally by observation of neutral weak currents and distinguished by the 1979 Nobel Prize in Physics. The expansion of universe, that is dark energy. While accelerators have confirmed most aspects of the standard model by detecting expected particles interaction at various collision energies, No theory reconciliation general relativity with standard model has yet been found. Cosmology may be said to have become a serious research question with the publication of Einstein's general theory of relativity in 1915, although it did not enter the scientific mainstream until the period known as the golden age of general relativity. About a decade later, in the midst of what was dubbed the Great Debate, Hubble and Slipher discovered the expansion of universe in the 1920s, measuring the redshifts of Doppler spectra from galactic nebula using Einstein's general relativity. Higgs boson. On July 4, 2012, physicists working at CERN, Large Hadron Collider, announced that they had discovered a new subatomic particles greatly resembling the Higgs boson, a potential key to an understanding of why elementary particles have mass and indeed to the existence of diversity of life in the universe. And acoustic, geophysics, astrophysics, aerodynamics, plasma physics, low temperature physics, and solid state physics joined optics, fluid dynamics, electromagnetism, and mechanics as areas of physical research. In 20th century, physics also become closely allied with such fields and electrical, aerospace, and materials engineering. The physicists began to work in government and industrial laboratories as much as in the academic settings. Following World War II, the population of the physicists increased dramatically and came to be centered on the United States, while in more recent decades, physics has become a more international pursuit than at any time in its previous history. Thanks for Wikipedia. Thanks for watching. Please subscribe our YouTube channel.